Single phase full wave rectifier based on bridge rectifier. In the previous video, we have introduced an example for single phase full wave rectifier based on center tap transformer. Now we are going to present another configuration for full wave rectifier based on bridge rectifier. In the bridge rectifier, we are going to use a conventional transformer with single primary and single secondary, and the output of the secondary would be connected to the diode arrangement like this. It should be noted here that all the diodes have the same direction, and we are connecting these two diodes from their center and these two diodes from their center, and from the output node and the earth here, we are going to connect the load or the resistance. In this case, the secondary voltage of the transformer can be represented as a sinusoidal waveform of Vm sine omega t, as we have mentioned in the previous case. Let us see what is the mechanism of rectification in this case. Assuming that we are in the positive half cycle. In the positive half cycle, this would be positive and this would be negative. So when this is positive, this would be connected to the anode of diode 1, but connected to the cathode of diode 4. So diode 1 would be turned on, but diode 4 is turned off. So the current will flow through diode 1 going to this direction. When the current passing through diode 1, this node it would be positive, and this node it is connected to the cathode of diode 3. So diode 3 would be turned off. So the current will not flow through diode 3, but will flow through the resistance R. Now the current is going to the resistance R in this direction. Alright? Now at this node, we have two diodes, diode 2 and diode 4. We already said that diode 4 is off because it is connected to the positive from this side. Let us see diode 2. Diode 2 is positive here because the current is coming from this side, is positive here, and on the other hand it is negative from the other side. So in this case, diode 2 is turned on. So in the first half cycle, the current passes from diode 1 to the load, to diode 2 to the transformer. Alright? Now, in the second half cycle, the voltage is converted such that this would be negative and this would be positive. When this terminal is negative and this terminal is positive, let us start from positive. If this is positive, diode 2 would be turned off because the positive here is connected to the cathode of diode 2. But diode 3 is turned on because the positive here is connected to the anode of diode 3. Now the current will flow from diode 3. It can pass to diode 1 or can pass to the resistance. Actually, this would be positive here. So this positive voltage would be connected to the cathode of diode 1. The diode 1 will be turned off. So the current passing through diode 3 will not find any path except the resistance R. So it will flow from the resistance R. Now it is going here. As I mentioned, this is positive now. So diode 2 is turned off. The current will not pass through diode 2. So it will continue. Now diode 4, the current is passing in this direction. It is in the forward direction of diode 4. So diode 4 is turned on and passing to this node. This node is actually negative in the second half cycle. So this is going to the negative side. This means that in the negative half cycle, diode 3 is turned on and diode 4. Diode 3 and diode 4. Okay? So the output in this case would look like this. At the first half cycle, the signal passes through diode 1 to the resistance to diode 2, and this would be positive and this would be negative. In the negative half cycle, this would be positive. It would be passed from diode 3 to the resistance, and this would be positive, to the resistance, pass through the resistance to diode 4 to the negative here. So once again, according to the load, this would be positive half sinusoid. So either in the first half cycle or the second half cycle, both of them will have a positive sinusoidal, half sinusoidal in the output at the resistance. The peak value at the resistance would be V maximum of the source itself. Now let us look at the voltage or the reverse voltage at the diodes when it is in off state. At off state, assume that this is positive and we have peak value V maximum here passing through this diode. The reverse voltage at diode 4 is V maximum, because actually we are going to this, assuming that this is the ground. So this is the maximum voltage passing through the diode 1. For diode 4, the maximum reverse voltage is minus V maximum. So in the first half cycle, the maximum reverse voltage in V diode 4 is minus V maximum. In a similar way, the current passing through this resistance here, the maximum the maximum reverse voltage at diode 3, here we have positive voltage passing here, so diode 3 is reversed here, and the maximum value at this point is actually the V maximum minus V maximum. So V diode 4 and V diode 3, the peak value in the reverse is only minus V maximum, not twice the value as in the case of center tap transformer. That's why in the case of full wave rectifier, bridge rectifier, the reverse voltage is less than in the case of center tap rectifier. So I'm not afraid that the diode will reach the breakdown voltage. This is actually one of the main advantages of the full wave rectifier bridge. However, the disadvantage is that instead of using just two diodes in the case of center tap rectifier, now we are going to use 4 diodes. So this would be slightly expensive than the center tap rectifier. Alright. In the second half cycle, diode 1 and diode 2 will be turned off, and the peak voltage of the reverse voltage would be also minus V max. Okay. Alright. This is an example for, or 2 examples. The previous video and this video are 2 examples for single phase full wave rectifier circuits.